So let's see, what we're doing today is kind of a combination of 7.1 and 7.2. So the first thing I want to do is give us just a quick reminder about the type of problem we did for the opener, about ratios and proportions, because we're going to be using those a lot in chapter 7. So a ratio is just a ratio is comparing two things using a fraction. And usually we write something like A over B. We could also write A to B. That's what the little colon means. Or we say A to B. So we're comparing A and B using a fraction. We usually, not always, but usually use the same units for A and B. But we don't always use the same units. So an example of when we wouldn't use the same units when we're using a ratio is like on a map. They say 2 inches equals 1 mile. So our ratio is inches on the map and miles in the real world. So we don't necessarily always use the same units. And we usually want to write our ratio, our fraction, in lowest terms. So we reduce our fractions. We can also talk about what we call an extended ratio. An extended ratio is when we compare 3 or more things. And we would write something like A to B to C. So for an extended ratio using 3 things. And this gives us the ratios, just breaking it apart. We have the fraction A over B, A over C, and B over C. So and we'll use these extended ratios a fair amount when we talk about polygons. So what we're going to do is use ratios to write what we call proportions. So ratios are these fractions where we're comparing things using fractions. Proportions. Proportions are when we make an equation with 2 ratios. So proportions are equations between ratios. So that's what we had on our opener. And proportions are what we're going to use over and over and over in chapter 7. And we decided on our opener, we solve by cross multiplying. So let me do a couple of quick examples here, just as a reminder. So we have kind of like our opener, 3 over 8 equals 5 over x. Some of you may have learned some different ways of solving these. I know a lot of my students last year talked about the fish. The problem with the fish is, what I saw was a lot of students couldn't remember how it worked, and the fish doesn't necessarily work for every kind of proportion that we need to solve. So if you have some other technique for remembering how we do this, I would recommend, what I'm going to say over and over is we cross multiply. So we're going to cross multiply to solve these. So I'm going to multiply across here and I get 3x, and multiply across here. 5 times 8 is 40, and then I divide by 3, and I get x equals 40 thirds. And we could do some other techniques, but there's little things we have to remember for the other ones that make them easy to forget. If we remember cross multiply, that's going to work every single time. One thing to be careful of is if we have a proportion where we have something like x plus 3 as part of our problem. I'm going to say that's 5 over 6. What I recommend we do whenever we have a quantity like this, put parentheses around it. To remind yourself that when we cross multiply, I have to multiply that entire thing by 6. So when I cross multiply, I get 6 times x plus 3 equals 5 times 12. Because what a lot of times students will do is they'll forget these parentheses and they'll write 6 times x plus 3 and forget to multiply, forget to distribute. We want to multiply by the entire quantity. So then I'm going to distribute, and I get 6x plus 18 equals 60. I subtract 18, and I get 6x equals, what do we get, 42? Divide by 6, and x equals 7. So the important thing to remember here is I recommend putting the parentheses around so we remember to multiply that entire quantity. And our setting up a proportion is going to be our big technique that we're going to use in Chapter 7. If you're in doubt in Chapter 7, set up a proportion. All right. Sometimes when we work with proportions, and this will come up as we go on further in the chapter, we get a quadratic equation. So I want to remind us how we deal with quadratic equations. They come up when we're talking about proportions. We'll talk about right triangles. In the next chapter, they come up a lot in right triangles. So, and when we talk about circles later, they come up a lot in circles. So we need to remember how we work with quadratic equations. So when we have a quadratic equation is something that looks like ax squared plus bx plus c, and we always want it to get equal to 0. So when we have an x squared, an x, and a number, that's when we have a quadratic equation. So an example of when one of these might come up is if we have the proportion x minus 3 over 3 equals 2 over x plus 2. And notice I put my parentheses around right away. So this is an example where my students last year that said, oh, you do the fish. The fish isn't going to work for you on this one. What we want to do is cross multiply.
What is the fish?
Fish, my son does it in middle school. You do they always draw a picture like this and say, this is what you do. And I said, well, what is it? So it's supposed to be a picture of how you multiply them out and how you divide. But they always forgot how it worked, and I never learned to fish, so I didn't even know. So you'd say, okay, you multiply by 2 times 3, and I can't remember how it works. So they'd say, oh, you do the fish. So that's just an example of a technique that people have learned that sometimes I can't remember how it works, and a lot of times they forget how it works. So let me get rid of that. So we're just going to cross multiply. So when we cross multiply, I'm going to multiply these two together. X minus 3 times x plus 2. And when I multiply these together, I get equals 6. Now when I multiply these two, what do I have to do? Remember? Distribute, and our way of remembering was FOIL. You have to FOIL this. So my first, x times x is x squared. Outside.
Mr. Green, I think it's a really handy thing too to let them know like Miss Hine does it in her class. If you put the FOIL down the side and you fill in those blanks, they don't miss it out.
Oh, so you write it.
And then you just put your x squared next to your f.
Oh. So our first, x squared, outside, 2x. So I'm going to put a plus 2x here. Inside, minus 3x. And the last, minus 6. And that equals 6. Anytime we have a quadratic equation, we want to get, where we have an x squared, an x, and a number, we want to get everything on one side and a 0 on the other. So I'm going to combine my like terms. X squared, I have a plus 2x minus 3x. So that gives me a minus 1x. Minus 6 equals 6. And I want to get a 0 on this side and everything on this side. So I'm going to subtract 6 from that side. So I get x squared minus x minus 12 equals 0. Now when we have a quadratic equation like this, where we have x squared and x and a number equals 0, we either have to factor or the quadratic equation. Whenever that's the only way that we know how to solve these. We either factor or we use a quadratic equation. If our numbers are nice, we can factor. So by factor I mean we set up our parentheses. To get an x squared, I get an x and an x. Some of you may have learned the cross and the box, that kind of thing. If that helps you remember how to do this, that would be one way you would do it. But our idea is we want two numbers that multiply to negative 12 and add to get negative 1. So that's going to be a 3 and a 4, and I get a minus and a plus. 3 times negative 4 is negative 12. Negative 4 plus 3 is negative 1. What's that? We have to, when we FOIL this, we have to get our x's to add to negative 1. So our two numbers have to add to this negative 1. Now we break this into two equations. This tells us that x plus 3 equals 0, or x minus 4 equals 0. Subtract 3 from both sides, so this tells us x equals negative 3, or add 4 to both sides, x equals 4. So we get two answers to this proportion. X equals negative 3 or x equals 4. So this one we could factor. Sometimes we get messy numbers, doesn't turn out nice, and we have to use a quadratic equation. So let's look at a quick example of how we use a quadratic equation. So we have ax squared plus bx plus c equals 0. That's our quadratic equation. When we use a quadratic formula, the quadratic formula tells us x equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. And the a, the b, and the c come from our equation. A is the number in front of the x squared, the b is the number in front of the x, and the c is the number that's by itself. So let's look at an example of how we would use the quadratic formula. Now this is all stuff that you've seen at one point or the other, so this should be a little bit of a review. So let's say we have 2x squared minus 10x plus 11 equals 0. I have my x squared, x and a number equal to 0. That's A, that's B, and that's C. So the quadratic formula tells us that x equals negative b. I'm going to plug everything in, negative 10 plus or minus the square root of b squared, negative 10 squared minus 4 times a, 2, and c, 11. And all of that is divided by 2 times a, or 2 times 2. If you plug your numbers into your quadratic formula like this, it's less likely that you're going to make mistakes with a plus and a minus and that kind of thing. So I'm just going to carry through here. Negative 10 is positive 10, plus or minus. Negative 10 squared is 100. Negative numbers squared are always positive. Minus 4 times 2 times 11 is 88. All over 4. Keep going. X equals 10 plus or minus the square root. 100 minus 88 is 12 over 4. And we simplified radicals in the last section. We talked about simplifying radicals. Square root of 12 is 4 times 3. So this is going to be x equals 10 plus or minus 2 square root 3 over 4. And then we can reduce this fraction because we can divide everything by 2. So x equals 5 plus or minus the square root of 3 divided by 2. So we get two answers here. X equals 5 plus the square root of 3 divided by 2, or x equals 5 minus the square root of 3 divided by 2. So those would be our two answers for x for this equation. So whenever I get a quadratic equation with an x squared, an x, and a number equals 0, I have to either factor or use the quadratic formula. One of those two. That's what we have to do every time. On page 439 of your book, part of our homework comes from page 439. They do a couple more examples using factoring and using the quadratic formula. But solving these quadratic equations is going to be something that we do as part of our problems that we do in geometry from here on out. All right. So now we've talked about ratios, proportions, solving quadratic formulas. Now we can actually talk about similar polygons. Hi, Miss Ross. So let's actually talk now about similar polygons. We're going to use ratios and proportions when we deal with similar polygons. So when we say two shapes are similar, we mean that they have the same shape. But not necessarily the same size. Our symbol for similar is one squiggle. And we read that it is similar to. The one squiggle means similar. polygons, that's what we're going to talk about, are similar if corresponding angles are congruent and corresponding sides are proportional. So this is where our proportions come in when we talk about similar polygons. So let's draw a picture of what we're talking about here. So here are my two polygons. And let's remember really quickly, what do we mean when we say corresponding angles and corresponding sides? What are we talking about when we say they're corresponding? We talked about it when we talked about a lot when we talked about congruent polygons. We said side A corresponds to side B. What are we talking about with those two figures? Do you remember? Corresponding means kind of in the same place on both of them. So they're the ones that we compare. All right, so let's call this polygon A, B, C, D. And this one G, H, I, and J. And we're going to say that polygon ABCD is similar to G, H, I, J. This tells us that angle A is congruent to angle G. Angle B is congruent to angle H. Angle C is congruent to angle I, and angle D is congruent to angle J. So our corresponding angles are congruent. Our corresponding sides are proportional, means that the length of AB over the length of GH is the same as the length of BC over the length of HI, and that equals the length of CD over the length of IJ, and that is the same as the length of DA over the length of JG. So if we make ratios of any of the corresponding sides, the sides that match up, the sides that are in the same place, we make those ratios. The ratios of all the corresponding sides are exactly the same if our polygons are similar. We call this the similarity statement. Just like we had a congruent statement when we had congruent polygons, this is our similarity statement. This tells us how the parts match up. Angle A matches with angle G, angle B with H, etc. And then if we take two at a time, it tells us how the sides match up. AB matches with GH, BC matches with HI, CD matches with IJ, etc. And we can make ratios with those corresponding sides. And if they're similar, all the ratios of the corresponding sides are the same. We can use any of these ratios give us the scale factor. So what we're saying is if AB over GH is 1/2, the scale factor is 1/2. So this would be half as large as this one. The sides would be half as long. So we're reducing its size by half. If our ratio turns out to be 3, that would mean that this one is 3 times bigger than the other one. Everything is 3 times larger. So we call that our scale factor. So anytime we're talking about similar polygons, we're going to be dealing with these ratios, and we're going to set up proportions to solve our problems. So let's look at a couple of examples, and then we'll be done. So similar polygons, our angles are congruent, our sides are proportional. All right. So let's say we know that triangle QRS is similar to triangle DEF. I want to answer 2 questions. What angles are congruent? So let's answer that one first. So if these 2 triangles are similar, what angles are congruent? So angle Q is congruent to which angle? Angle, which one? D. Angle R is congruent to which angle? E. And angle S is congruent to angle F. That's the only thing that's left. So we do this just like we did when we talked about congruent triangles. We're just matching them up. They're in the same place. Q and D are in the same place. R and S are in the same place. Sorry, R and E, same place. S and F are in the same place. And now I want to say what sides are proportional. Well, the fact that these 2 triangles are similar tells us that those angles are congruent. So yeah, I want to know which sides match up between the 2. So we want to match them up. So side QR matches with which side on this triangle? DE. And that's going to be side RS matches with which side on this triangle? EF. And that ratio is going to be the same as side QS matches with which side on this triangle? DF. So those are our proportional sides. If we made these ratios, they would all be the same because the triangles are similar. Questions there? All right. Now, go back, yes? So we're just matching up the sides that are in the same place, the angles are in the same place. Just like we did when we talked about congruent triangles, congruent polygons. Now for this example, we want to know, are the triangles similar? And then if so, we want to write a similarity statement. So here are my triangles. And these are not to scale. And I'm going to call this triangle ABC, and this triangle DEF. So to show that they're similar, to know that they're similar, we need to know 2 things. Are the corresponding angles congruent? Well, let's see. Angle A is congruent to angle E. angle B is congruent to angle F, and angle C is congruent to angle D. So we have three congruent angles. So corresponding angles are congruent. So we're okay on that part. So I'm going to say check. Now we need to see if the sides are proportional. So I'm going to say angles congruent. Yes, we check that out. The angles are congruent. Sides proportional. So we need to match the corresponding sides. So which side is going to correspond to side 34? 17, because it's the hypotenuse. It's also the longest one, right? This is the longest one here. We need to compare it with the longest one there. 34 over 17 equals what? 2. Now let's try 30. 30 is going to compare with 15. That's the medium side. Equals 2. And then we have 16 comparing to 8. And that is 2. Check. So yes, they are similar. Use my symbol. Yes, similar. And we're going to write a similarity statement. So triangle DEF is similar to triangle. What angle matches with angle D? C. What matches with angle E? Which one? CAB. So that would be our similarity statement. Triangle DEF is similar to triangle CAB. Now, if all the angles were congruent, but even one of these was different, if this turned out to be 2.1, then the triangles would not be similar. They have to be exactly the same. So our angles are congruent, our sides are all proportional. Same ratio between all the sides. All right, one last quick example. And I don't want to say equal, I want to say similar. And here are our polygons. So this is W, X, Y, Z, and this is R, S, T, Z. 16, X, 24, and 20. And we want to find X. These two are similar. So what do we know about the sides? The sides are proportional. So we write a proportion. So which side of this polygon is going to compare with X? 20. It's in the same place, right? So X over 20 equals, and which side is going to compare with side 16? 24. X over 20 equals 16 over 24. I could also set it up as, I could write the proportion, the ratio here. I could say 16 over X equals 24 over 20. And I get the same thing. When I cross multiply, I get 24X equals 20 times 16. So 24X equals 320. Divide by 24, and X equals about 13.33. Possibly, you can possibly get weird numbers. So when in doubt, write a proportion. All right, homework, quickly. Page 439, number 2 through 12 even. Those are all of our quadratic equations. And page 444, number 10 through 24 even, and 30 through 46 even. All right, there you go.